Very good. Good afternoon, everyone. It's a pleasure to introduce today's speaker, LianTao Wang, who's visiting us from the University of Chicago. LianTao is visiting on account of his, among other things, on his application for the senior position at FTPI. And LianTao has received his PhD from University of Michigan in 2002, and then after two postdocs at Edison and then Harvard, he took a junior position at Princeton, and after a few years moved to Chicago as a faculty member, where he rose to the ranks of full professor. LianTao is well known in many parts of high energy theory community, working on collider physics in his early days, on supersymmetry, on newly emerging topics of dark sectors, dark matter phenomenology, but also in the recent years, increasingly more so on cosmology. And today's talk is on gravitational waves. Please, take it from here.
Thanks for the invitation. It's a pleasure to be here. Yes, I'm talking about the gravitational waves and the window into the early universe. So just to set the stage, let me just briefly give you a very brief overview of where we are in terms of particle physics and our understanding of the universe. So there are two standard models. Okay, there's a standard model of elementary particle physics, and I think cosmology also has a standard model. Sometimes goes by the name of lambda CDM model. So something along those lines. And I think combining these two models, we explained almost all the data perfectly. Yeah, I put the quotation mark there. There may be a couple like tantalizing tensions, but other than that, there's and we explained all the data among these two models. So are we done in this sense? And of course, we are not. And there are many open questions. I won't read this list to you, but I think you have probably seen this somewhere as well. But a lot of the underlying questions about why we have this structure that all among these two standard models are unanswered. We want more answers. And of course, we need to do that. We need more data and more insight. Okay, so.
Excuse me to interrupt you. I'm sorry, but you're only showing.
Road ahead. I think overall we're a bit confused. Like what exactly will be the next thing to come? I think we're a bit confused. So we are trying we're looking at many different directions, trying various different things, just to again in a very broad brush way. So we can think about higher energy colliders, right? So we are currently about hadron collider. We can also there are also active effort thinking about what will be beyond that, even higher energy. There is also we can do better search. Like for example, we can make a lot of particles, trying to look for very rare processes. This sometimes for the high intensity frontier, and we can also do better search in the sense that we can try to develop new experimental techniques, such as using the new quantum technology and so on. That's another very active direction nowadays. And we can also try to have like new ideas, theoretical insights, like new ideas, such as the new ideas from generalized global symmetry and so on. And the question is, are they sort of going to solve some of the questions in particle physics or not? I think the jury is still out for that question. Yeah, it's a question that I'm quite interested in. And then also we are going to similarly higher energy frontier, but in a different venue that's looking towards the early universe. We also know the early universe dynamics happens at a much higher energy than any terrestrial experiment. So this is the part I'm going to focus on. I worked on several of these aspects, but I'm just going to focus on this in this topic. Just to again set the stages here. Here is a way to representing our understanding of the history of the universe. And this blue line here is what we call the cosmological horizon. And it depends on these are the three stages of the evolution of the universe. The first stage is the inflationary stage. Okay, the whole moving horizon actually shrinks. And then the universe went through a hot Big Bang, and then we went through presumably a radiation-dominated era. Then we went through equality and the matter-dominated. So this is a very broad brush way of representing the history of the universe. So, and this is what we think the universe, how the universe evolved to, approximately. Okay, the question is, now the question you can ask, what do we really know about this picture? Okay, so what we know is, first of all, at the very large scales, we have a CMB measurement, a large scale structure measurement, and there will be more to come in the future. But broadly speaking, we have some knowledge about the large scale structure. And presumably this is coming from some early stage of inflation where the perturbations are generated. So we know this period. Okay. No doesn't mean that we're 100% sure, but at least we have some knowledge about it. And for smaller scales, we don't, because the evolution of the universe becomes nonlinear, and we are limited by our power in predicting how these nonlinear dynamics. What's the prediction of those nonlinear dynamics? We can try to numerical simulate it, but it's not as powerful as the large scale. So there are lots of room, and then there are lots of unknown for what happened at the smaller scales. And on this axis, we think we know what happens at the Big Bang synthesis. Okay, and there's beautiful theory and the data and the big batch. Okay. And afterwards. Okay, so our knowledge of the universe and covers this period. Okay. So before that, we don't quite know, because the problem is that we observe the universe with photons, roughly speaking. And but here is dominated. This part of the universe is dominated by thermal equilibrium. Okay, once you enter thermal equilibrium, it becomes opaque, and it's insensitive. You lose information of the history. So that's why our observation of photons does not tell us enough about what's happened before. Obviously, the open question is what happens both in the period after reheating in early universe and the period of inflation after the large scale structure is generated, but before the end of it. These two are the major open questions. Okay, major gaps in our knowledge of early universe. Here is where gravitational wave comes in. So in recent years we have a remarkable discovery of gravitational waves. I was really shocked that they actually managed to detect such a feeble signal with such an intricate instrument. And this is LIGO detection of merger, binary mergers. And then more recently, I think in 2023, the NanoGrav reported the first observation of the so-called stochastic gravitational, and also a bunch of other So these data are still, in particular, this kind of data is still quite, in terms of trying to use that to understand what happened in the early universe, is still quite initial data. But we don't know whether this is coming from actually from early universe or from late universe. Okay, but But nevertheless, I think that the discovery of gravitational waves are very exciting, and it does open a new window. So if you want to find historical parallels, so I can think of two. One of them is the invention of a cyclotron by Lawrence. I just learned that he's actually an undergraduate here, and also the NCS and Wilson's discovery of CMB. By the time of the invention and the discovery, I think these things, at least from nowadays standard, don't really tell us anything that interesting. The accelerator is very small, and they just see some unexplained white noise. But little that we know, that later on in the later decades, both of this developed into high energy colliders, this developed into a rich, very rich area of cosmic microwave background physics, which teach us enormous amount of early universe. So I believe that we could be at a similar historical juncture because of the gravitational wave. Okay. So this is my intro. And of course, the benefits of gravitational wave is that it does not suffer from the thermal equilibrium problem. The early universe becomes transparent to gravitational waves. It carries directly the information of the universe, the dynamics of the universe, when gravitational waves. Yeah. And that's why this is could be in principle very informative. So the question is, what are we looking for? Okay, let's see. We are looking for obviously early universe signals. What are we looking for? So one set of signals is coming from this period. This is called the post-inflationary period. There are quite a number of works already, and this is just a typical picture of what people describe what could happen post-inflationary. And typically you need something quite dramatic. And so sorry, I should say this is the strength of the gravitational wave signal measured in it's a relative gravitational wave abundance. And this is the frequency of the gravitational wave. You see many of this kind of plots later. So these are various predictions for various scenarios, and these are the reach for many either current or future gravitational wave probes. Okay, so these are phase transition. These are the first order phase transitions that happened in the early universe. It's quite a violent process. It will be violent enough to generate observable gravitational waves. And this is, for example, is those one of those topological defects called the cosmic strings. They vibrate and radiate gravitational wave. So,
But is there any operational way of saying that all of this background is from phase transition or not?
Phase what?
From phase transition, right? From collision of the
yeah, you
bubbles.
mean once you see the stochastic
Right,
signal.
like if you see the binary, you know what's going on, right? But
Yeah, so first of all, you still hope to try to get some direction, even though for the background, as much as possible to distinguish your background from the real stochastic gravitational wave signal that come from the universe. And also these signals typically has a different spectral dependence than the background. So that's the hope.
So you both mentioned phase transition. So
Ah.
phase transition from what to what?
vacuum to vacuum.
So for example, electron weak phase transition. Okay, the phase transition that gives the universe on mass.
Okay.
Yeah, it can be both either first order or second order. The ones that produce the cosmic strings are typically a second order phase.
Actually, sorry, to be clear, so these are predictions based on, essentially standard model physics, like, or how model dependent is what you're gonna see?
This is a very model dependent. Okay, these are particular models. Of course, we are speculating. Standard model does not. If you just have standard model particle physics, it does not have a first order electric wave phase transition. So this is the, if this is the electric wave phase transition, it has to be beyond the standard model. Okay, and the standard model by itself does not have cosmic strings. Okay, but the string at this energy is the tension is way above the standard model. Okay, I think we are anticipating there are rich new physics and it's way above.
But maybe this is not entirely relevant, but why does the inflation curve have a kink? I would have thought that there should be scale invariant, just like the temperature perturbations. Is that not true?
Sorry,
Like the blue line, like turns, it changes slope.
so this you mean this?
Yeah, where
This
does the
is
shape?
the inflationary tensor.
No, you see the frequency 10⁻17 hertz. This is related to the inverse lifetime of the universe, I think, because it's 10⁻17 seconds. So
okay.
that you probe a smaller fraction, I think.
Okay.
Well, the question is why this curve bend like that?
Well, so the gravitational wave generated from inflationary fluctuations, right? Once they generate, they redshift. Okay, so even if they are scale invariant at horizon exit, they won't be scale invariant. Propagate to us.
Oh, okay. Sure. Yeah.
Okay. So I wanted to, that's not what I want to focus on. Okay, so the one I focus on is this area. Okay, which is there's less work during the inflationary era, and but there are certainly also interesting physical processes that could actually generate interesting gravitational waves. Okay. But just to again a basic point. So just to see that what kind of frequency that this kind of gravitational wave is, because our detectors are usually geared towards a certain, depends on the size of the detector, geared towards certain frequencies. So here I'm measuring when the gravitational wave signal is generated from its distance to the end of inflation. Okay, so here are 60 EFO from the CMB scale to the end of inflation. But let's say the something happens, generates gravitational wave. That something happens, 40 EFO before the end of inflation. That give you roughly 10 to the minus 9 nanohertz frequency. Okay, and the rest to us. And when something happens, roughly 20 to 30 EFO to the end of inflation. That give us roughly 10 to the minus 4 to 10 to the minus 2 hertz. This is in the ESA band. And when it's getting closer to the end of inflation, 10 EFO, this is in the frequency range of LIGO, Einstein telescope. So this is just to say that I haven't talked about any of the mechanisms, but this is just to say that we do have a set of instruments that's sensitive to this kind of physics. Now I'm going to start talking about some of the sources. So this is just, of course, there are many possibilities. So I'm going to just trying to tell you a few stories. I probably have too many slides, so I'll just try to give you the gist of it. I will try to, maybe if necessary, I'll skip some details. Sorry about that. And so the first one is I want to talk about is the so-called secondary gravitational from a spectator scalars. Okay, so this is the story is following. Okay, so during inflation, right, we know there is inflation that fluctuates. That's the one that generates the quantum fluctuation and become the seed of the structure we see in the universe. But at the same time, many other fields could also have quantum fluctuation if they are light enough during the inflation. Consider space, everything fluctuates. So those fields could, in principle, source curvature perturbation, additional to the ones that sourced by the inflation. Okay, when those curvature perturbations evolve, they will evolve outside the horizon and it froze. And then they will evolve back into the horizon. They will start oscillating again. Okay, when the curvature perturbation is oscillating, and they can be contributing to the gravitational wave as the source on the right hand side of Einstein. So this is going to generate gravitational wave when those perturbations re-enters. All right, this is sometimes called a secondary gravitational wave because even though the physics that generates the gravitational wave happens during inflation, the gravitational wave itself is generated later. The seed was generated earlier, and the signal was generated later.
So it's a decay of the scalar perturbation.
Yeah, it's just the scalar perturbation source, the gravitational wave, decay as a result.
And what
Slowly.
determines the polarization?
That's just I would say it's largely unpolarized. This is just the equally polarized. If it is a scalar perturbation, not any of those special ones.
Well, if I have a scalar mode with a given K and I produce a gravitational wave, which way would it, how do I picture it?
I would say either way. I don't think that there is a preferred direction. No, yeah, but there is a one way to generate polarized gravitational wave, like R wedge arc.
But are you imagining very large fluctuations?
Let's see. I'll go there. Okay. I'll go there. Yeah. Yes. I'll show you why.
Yeah,
is
because
that.
typically delta rho to rho is really small. Right?
Yeah, at the large scale.
Yeah.
Okay, at the large scale.
Okay.
So all right. So yeah, this is basically a picture that what I just said. Okay. So this is scalar perturbation is generated, and this is the horizon entry. Before that, you don't get gravitational wave, and at the horizon entry, it start to generate gravitational wave at the same time that the scalar perturbation starts. This is basically, and yeah, this is just the numerical evolution gravitational after horizon. You can see that decaying, but it also oscillates. It's this oscillation that generates the gravitational wave. Okay, so now let's understand some properties. Try to understand some properties of this density fluctuation. Okay, so the picture of inflation, because inflation stretches any of these perturbations. The picture is that when the mode is inside the horizon, so I'm just drawing a rough picture. Is each of these box is supposed to be a horizon volume size H inverse, and when the fluctuation is inside the horizon, it generates basically a scale invariant perturbation size of H, and the quantum fluctuation. Many they look identical in my picture, but they're actually random. Okay, so but on the other hand, when the mode being stretched beyond the horizon, they behave classical. Okay, so the picture is there's some. If I look at the super horizon mode, I have some classical field, and I have a random kick on the small scales. Okay, so that's the picture. Okay, and this picture can be systematically modeled, and you can write a Fokker-Planck equation for that kind of. So this is basically the probability of finding the field value at the sigma, the evolution as a function of time. The first two terms is basically the classical evolution of the field. The last term is basically like a diffusion equation. This is the last term is basically a random walk. Okay. So because now if you solve this equation, you get this probability distribution. You can start to calculate the power spectrum. Okay, the 2-point correlation of the fluctuation. Okay, so that let's just take perhaps the simplest model, like a scalar field, single real scalar field, which with the mass and the self interaction. Okay, that's perhaps the simplest one. I'm just going to assume there is such a field in addition to the infloton. And okay, so for light field means that this mass of this field is much smaller than the Hubble. Okay, it's smaller than the Hubble. Okay, so there are two kinds of limits. The first, more familiar limit is this massless limit. This will be like similar to the axion. In that case, the field is actually stuck because of the friction. It's stuck somewhere, and it fluctuates around. There's a flat potential, and it is flat fluctuates around. Okay, again, the famous example is the misaligned axion. And on the other hand, the second limit is that the same but still light. Let me be slightly more precise what I mean.
What do you mean fluctuates around? If it's stuck, it's stuck.
Well, it still has quantum fluctuation.
Okay.
Yeah, classically it's
Yes.
stuck. Yeah. So let me just be slightly more precise. So again, at the large scales, we said it is governed by the classical equation motion. So this is the classical equation motion of the field. I'm assuming just a massive field. And for this discussion, I'll temporarily ignore the self interaction. And we can integrate this equation. This is the solution, okay, of the equation, where this is the initial value of the field. And again, you can the behavior depends on what you estimate for this, but both on dimensional background and all, you can try typical models, and this is roughly on the order of 1 over h dot. H dot is the evolution of the Hubble constant. Okay. And therefore, this is in typical inflation, this is proportional to the slower parameter. Okay, so therefore, if the mass square is bigger than the slower parameter 10 times the Hubble square, and you see that in that case, the initial value of the field doesn't quite matter. Okay, what this means is that this field settles into a fluctuation around sigma equals 0. So that's what I mean by massive but still high. Okay, of course, when this mass is much bigger than Hubble square, then it's it just stops. That's a different regime. Okay. Yeah, so this is what I just said in the picture. So the field will be in this regime that I'm interested in. It's going to be stuck here. Okay, and then when you can solve the Fokker-Planck equation, you can try to calculate the spectrum and so on. Okay, but so this is the answer. But instead of showing you the answer, let me just give you some intuition. What that spectrum looks like. Okay. So here is how the perturbation evolves. So each of these lines is a perturbation corresponding to a particular wavelength. Okay, and when before the mode exit horizon, its fluctuation is the order h. Okay, it's set by h, and after the mode exit horizon, it starts to evolve classically. Okay, again in the simplest case, when evolution is dominated by its mass, this will lead to a suppression of the amplitude. Okay, and similarly for another mode, exit the horizon later. Okay, but of course, when you exit earlier, you have more time to evolve. You get suppressed more, and when you exit later, you have less time to evolve. You get suppressed less. Okay, so this is what we call. Yeah, so this is just in equations. What I just said. Okay, more damping for longer wavelengths. Okay. This is what we call a blue tilt, in the sense that you expect more powers on smaller scales. Okay. Again, so this is you can try to actually solve numerically the Fokker-Planck equation for that full interaction theory, and this expectation is one out. Okay, now what happened after the inflation? Okay, what happened after the inflation is that this field will more or less behave like matter field. They will still oscillate, right? So and so in this figure, this is radiation. The radiation dilute like A to the fourth, and then the matter field is horizontal. They dilute like A to the A cube. Yeah, and multiply rho by cube, so that matter-like behavior is horizontal. So this means that this field, even though it can be very subdominant during inflation, it could become important later on. It doesn't have to completely overtake the radiation, but can still be quite important. Depends. It could also overtake the radiation, and then it becomes a so-called curvature scenario. Yeah, these are just the mass equations for the words that I just said. And now for them to go to further. So when they become more important, then their fluctuation will leave a larger imprint on the curvature perturbation. Okay, that's the convection, which is going to source the gravitational wave. Secondary gravitation. Okay. All right. So here are some real studies. So these are some different scenarios corresponding to different cell interaction and so on. Okay, so this is the blue tilt I was talking about. This is the curvature perturbation. This is the blue tilt I'm talking about. Then we assume this field eventually decay. Once decay, it goes away. Okay, so why is this blue tilt important? Again, this is very obvious on this picture. So these shaded regions are the constraints from the large scale structure and CMB. Okay, that's we already measured, and that's the part I showed you very early. That's the part we think we already know. Have a quite good idea on those large scales. So on very large scales, because these guys are typically isocurvature perturbations, and it's very difficult to do anything add to it. So this is, but at the smaller scales, larger K, the perturbation can become very large. Okay, because of this natural blue tilt. Again, I hope I showed you that getting a blue tilt is quite generic. It's not something that you really have to work very hard on. Okay, so this behavior is quite expected even in this very simple model.
So on the pink region, is there a gap in the constraints?
There is a gap.
So what's the gap? Are we going to cover?
-4, something like the amount of, okay, I should say that in this picture, I'm assuming the scalar field does not dominate. Okay, it's not the curvature concept. Okay, in that case, this is isocurvature. This is subjective to isocurvature constraint on large scales. Okay, so it's pretty stringent. Okay, so a couple order of magnitude less than 10 to the minus 5. Basically the perturbation.
Okay, that's basically our observed fluctuations in the
Yeah. Here is the Planck constraint.
Yeah. So that's not, we're not going to cover there. It's observed value.
Yeah.
Always start there.
Okay. So again, so this is the blue tilt. Enters horizon and then decay.
How do I see the isocurvature constraints on this?
So let's see. Because this cannot be big, right? Because otherwise it added to the isocurvature. Okay, so this is the observed. This is the observed 10 to the minus 9. The 10 to the minus 9 is the observed adiabatic perturbation, right? So this, so if you blow this up, you will see exactly where it is.
But it should be quite dependent on lambda or m, right?
It depends on lambda. So there are different curves here. So they all start from a very. I assume they all rise quite. No, we pick the numbers here because it doesn't rise. Like For example, you can imagine that I blue tilt very strong if I start out from here, then it's go down.
Nice.
Okay.
Okay, so that top line is lambda of 0.05 or?
Yeah, so sorry. So there are two, let's go through this a little bit, okay? So I'm assuming that this field does not dominate. Okay, the amount of how important it is depends on this fraction. This fraction controls like how much energy density it occupies. So these are these two set of lines. So what is the marginal? So the 1/3 is the
Why does it induce spectral distortions of the scene?
I think it just the perturbation does not align with the adiabatic perturbation.
And the relaxation
Yeah.
gives,
Yeah, I think that translates into some of these fixed.
So when you say it doesn't dominate, so it decays at some point,
Decays. So we assume they decay at some point.
but decays before it gets.
Before it dominates. For this one, I'll get to the reason why we make that sound. Okay, it's a little bit artificial. I'll get to the reason why we make that sound for this figure.
And the fact that it's decaying, so it's coupled to other fields. And
Yeah.
doesn't that have effect on what happens early on?
So let's say it has a long lifetime with weakly coupled to standard model fields and so on. Yeah. So it doesn't, we're assuming that it doesn't otherwise have another effect. So from this, when these curvature perturbations re-enter the horizon, they degenerate the secondary perturbation. I will not show you all the equations, but this is the spectrum that generates. Okay, it broadly follows the spectrum of perturbation, which is not a big surprise. Okay. It is superimposed on some of the future probes.
Can this fit the nanograph?
It cannot do nanograph. For nanograph,
It's much higher.
yeah, let me make a comment on nanograph. And, yeah, so the nanograph is you literally need to do this. Very just shoots up. So that is I can take the parameter here, or take the mass larger because the top blue is depend on the mass basically, or the self-coupling, and I can literally take that and make it hit the nanograph, but that M is bigger than H, so it's outside of.
Yeah.
I shouldn't be using it. I have one more scenario that could, in principle, but my goal is not to explain it, if I could.
On this part, the usual slow roll inflationary model would be flat around on the next plot, I think.
Yeah, it will be like this. A little bit.
So actually, can you show the next plot? So on that scale, it will be somewhere around 10 to minus 14 or 15 in omega.
In omega.
Yes.
Yeah.
So that would be above the curves that you're plotting here.
No, this is the gravitational wave redshift. What generates?
Oh, I see.
Yeah.
No, but in omega, you would still have it. Would still be 10 minus 15, no?
It's not 10 to the minus 15. So when they exit the horizon, right, they froze, right, so and they enters, and then they can be becoming the oscillating again. Okay, so it was determined by when they enter.
No, what I'm saying is
Yeah.
in one of your earlier slides, you were showing the inflation background due to the amplification of vacuum modes.
Right. But that was the primary gravitational wave already generated during
Yes,
this session.
but that's sitting at 10 to minus
Yeah,
14
this
or
is
10 to minus
different.
15.
This is generated later, so it stopped oscillating later.
Yeah, but I think Fuchs' point is that
It will
if
be
it's
below-
much higher, how are you
Yes.
gonna pick this out from the inflationary background?
Yeah, the inflation
Where
background
the
would be above
horizontal
this.
line would be in the
Oh,
scale, right? That's the question.
Yeah, but you know, I think that the shape is different.
Yeah, but
That's the-
where would be, would it be above this triangular or,
So let's see the,
In one of the earlier slides. yeah. Yeah, here, so.
Yeah.
So the blue line is somewhere in 10 minus 15.
blue line is somewhere around 10 to the 8. You mean the
The
omega?
inflationary, yeah.
Yeah, so I think my hope is that, you know, you will see, you know, because maybe at this, if you do achieve this sensitivity level, you can see some of this.
It's comparable, yeah, to the
Yeah.
inflationary.
Is it the same quantity that's being plotted on the vertical axis?
It is the same quantity.
Because here it looks like
It's omega is gravitational wave.
because it looks like the experimental results are going far deeper than on the other plot.
They are different experiments. The other one that doesn't include all the experiments.
This is about right.
The other one is a very old
Uh.
law. The other one is a very, I just grabbed it somewhere else. Didn't make the other.
So is it fair to say, actually, for the green curves, F sigma equals 1, the peak of your spectrum actually equals what Wook was talking about?
Yeah, so.
That's where no peak happens, exactly.
Yeah, you need to reach this kind of sensitivity to get this. Okay. This is a kind of basic scenario. I'm not trying to say you do definitely see this. We made a few assumptions. Okay, I think perhaps the one important assumption we made is that this thing doesn't dominate. Okay, if this dominates, you will have a slightly, you will certainly have much better connection. Okay. This is artificial assumption. Actually, I'll explain it now why this we were making this. I made this. So a more general scenario will be that the matter actually start to dominate. Okay, this additional field actually dominates, and then decays. Okay, so and this is more general, and I don't stop it right before it decays. Okay, so so this will be really curvicon-like, a curvicon-like scenario. And for a larger this has a larger signal and it also has an interesting spectral shape. And the reason that this is hard is that to make this prediction, you need to track how the gravitational potential is evolving, because these are the source of gravitational wave. Okay, and in the case of radiation domination, okay, there's an analytical solution for that transfer function. Okay, that makes the numerical integration much easier, much easier. Okay? You can do it on the laptop. Okay, and in this case, you have to do it very hard. Okay, you can still do it on several laptops, a few weeks, but it's a very difficult because suddenly you have to numerically track how the gravitational wave is evolved. There's no analytic solution, and that's why this is harder, but we also did it. And you do see that so this is the result for if I assume pure radiation domination, and this is the result. You actually see this more general evolution. You do start to have this interesting spectral shape. Okay, so maybe I'll also tell you another slightly different scenario. Okay, slightly more complex. Okay, previously I was talking about a real scalar. Okay, now let me talk about a complex scalar. Okay, just one step further. Okay, and this is I view a complex scalar potential from top. Okay, this is a two-dimensional field space, and the circles are supposed to be the equal potential ones. Okay, so this field is parameterized by the two directions. One is the radial mode, the other one is the scalar direction. And in this case, and if the field is initially misaligned from the origin, right, this field will roll down. Okay. So the radial mode will become smaller. And okay, and but on the other hand, this field will fluctuate along the theta direction. Okay. Now, if you compute the delta rho over rho, all the spectrum of the curvature perturbation, you see that it's inversely proportional to the size of the radial mode. Okay, because the radial mode is, and then when the radial mode gets smaller, you actually get a very much lower. Okay, so this is different from the scenario before. Before is I'm relying on the fact that it will evolve classically when the scale exits the horizon. This one is just rely on the fact that this is rolling down. Okay, so this is I think we call it the rolling radial mode scenario. Okay. So the fluctuation, so this can in principle have a much bigger fluid.
Is this happening because, like on the previous slide, I think you had a mass term for the angular mode? It's like last term, there's like a mass term for the angular mode.
Oh, sorry, I should say that. I should say I'm assuming that the angular mode is not entirely flat. Otherwise, you will get a mass term.
And you explicitly made the mass dependent on S.
Well, this is just the m square phi square. Wow. So this is the size of this field.
Mhm.
Okay, the S times theta is the size of that field.
Okay. Yeah, and as it gets closer to the middle, the mass gets smaller.
Yeah, I'm making that assumption. Yeah, so this is the blue tilt you see. Okay, so it's much more blue tilted, and previously, if I push the other model to the extreme, it will violate the line. The assumption here is it's much easier to get a large blue tilt. So by the way, this flat piece is we're assuming that the potential the minimum is not at the zero. The potential is at the S equals FA. Okay, once you reach FA, you start to do like you just the fluctuation stop. The fluctuation stop to grow because the radial mode is fixed. So yeah, you have a much bigger gravitational wave signal. I didn't show you the nanogram. So I can even take this to the extreme and get a nanogram. That's huge. 10 to 10 minus 8.
Shifted right.
We can try. Yes. By the way, there's nothing really sacred about any of these benchmarks other than the fact that you have to make sure the theory is consistent. There are a lot of free parameters. We just pick something to show the typical size and there are these features because of the matter radiation condition. When should I stop?
You have another at least 10 minutes, 10,
Okay.
15 minutes.
Okay, I probably won't have time to finish the second story in detail, but let me just read the gist. So the second topic is this example is what about the topological defects? Topological defects can also generate gravitational waves, and this is actually a very old subject. You know, the standard textbook here, and And, but I think there are still many more to be done, and it's particularly interesting. I think that it will be potentially not the work that I'm done, but potentially in the future, this could be an interesting testing ground for some of these new theoretical ideas, because I think they are it's more natural to apply them to the topological defects. Okay. So not this work, but potentially there will be more. Yeah, so in particular, I'm focusing on this thing called the defect networks. That mean that you don't have one of the just generate one defect, but you generate a defect network. Okay, and I won't try to explain this this picture for you, but just to show you that in grand unification is this kind of. I'm not even going to talk about one of these models. Instead, let me just show you. Just to demonstrate some of the physics of the defect network. Let's just play with the toy model. Let's have two scalars, and they have U1 charge, 1 and 2, and they went through a phase transition at a different scale, V1 and V2. I'm going to assume that there's a hierarchy between these two scales. So I'm choosing V2 is much bigger than V1 in two stages. In the first stage, U1 breaks down to a Z2. Okay, you will generate strings because of this breaking, and then in the second stage, Z2 breaks down to nothing, and this will generate the domain. So this is going to generate a string domain one. So in particular, in this kind of model, there are two possible configurations of this string wall network, and the first one is that you have two strings both. So these arrows are supposed to telling you the phase of these two scalar fields. And it depends on whether they are rotating this way or that way, the string is either plus or minus. Okay, so these two strings are all plus. And because of this interaction term, the phase of these two scalar fields has to satisfy a relation. Okay, so the phase of the second scalar field has to be twice of the phase of the first scalar field. So if you follow that through, you see that the orange arrow are the phase of the first scalar field and so on. And there is a domain because there's a phase jump in the. So this is one possible string or network. You can also have a one plus minus string on the domain wall. So I'm going to imagine that these two phase transitions happens one of them during inflation, and that actually followed by another stage of inflation. Then I'll have the second stage phase transition. Okay. And this is my choice, but I think you see that it's not too hard to imagine that this can be happening. As I said, if first stage of phase transition happens during the inflation, and if the whatever the sector that does the phase transition does not dominate inflationary dynamics, the inflation will just continue. Okay. Then if these two have a big hierarchy, there's enough room to fit in a stage of a sustained inflation. On the other hand, there's also another natural realization to this scenario is by the first phase transition is followed by a stage of thermal phase inflation. See that can very naturally happen, and in particular, the second stage of thermal inflation also implies that the gravitational wave. We can talk about this a little bit more later. But to do that, let's just do some basic estimate of what the gravitational wave radiation of a string domain wall domain wall bounded by string. I'm going to, for this purpose, I'm going to assume that the radiation from the wall dominates. Okay, this is not very hard because the mass of the wall goes by the area, and the string goes by the perimeter. Okay, and there is some simple quadruple formula and so on. But the radiation of the wall is basically the wall tension divided by n plus. this is pretty easy to understand that what tension has to matter. You always expect the n plus because it is a gravitational wave.
Cosine to the fourth is.
It is some quadruple potential. And actually the quadruple. Yeah, and what's going to happen is that this thing we call a disk, and there's a string bounded by a disk. This is going to oscillate, and until for duration roughly corresponding to the lifetime of the wall inverse. Okay, so then it stops. And yeah, so this is just to estimate, and from this formula you can try to estimate what is the gravitational wave density. So this is basically the energy in the domain wall, and in this object, once this object is in the horizon, it redshifts like a matter. Okay, so that's that, and you divide it by radiation temperature of course to figure out what omega is. Long story short, and omega something like this. It depends on the temperature when the wall is produced, and it also depends on the wall tension. Now let's try to understand how this fit together with thermal inflation. Okay, so or fit with the second stage of inflation. And so I'm going to imagine, so there is a so the second stage of inflation is some second order phase transition, and when the scalar field gets a V1, okay, and this is the gravitational wave strength formula I just worked out on the previous page. You can write it as the following. For the gravitational wave to be large, okay, naturally you requires the height of this potential. The height of this potential here is larger than the temperature. Okay, the height of the potential here is larger than temperature. This means that at least when the field is here, okay, before it rolls down, completes the second order phase transition, the vacuum energy actually dominates. Okay, this means that you actually have a second stage. So that's just showing you that this kind of model, if you require large gravitational waves, and it's consistent with having a second stage of inflation.
This field was responsible for the first stage as well, or?
Another field is responsible.
And why is the field still there? The top, why is it at the top of the potential?
Well, so let me give you the thermal inflation story. Okay, so one story is that it can be supported there by the thermal inflation. The other story is there's some other like a.
But during inflation, during the first period of inflation,
Yeah,
what's the potential?
Inflation, presumably this is dead. This could be due to a thermal corrections. This also.
But there's no during inflation. There's no thermal.
Yeah, this also. Well, there is a. You can also assume that there is some kind of like a waterfall field that created this thing that started.
Okay.
And
Okay.
That's another possibility. Okay. And yeah. I think I said some of the things I wanted to say already. That it's particularly easy to arrange if this is realized by the second stage for thermal inflation. What's typically needed in this thermal inflation scenario is I need a flat potential, relatively flat potential, and lifted by higher order. Particularly easy if you aficionados of SUSY. Okay. If you want, I can show you a SUSY model. I think when I was a student giving talks, that anytime I show a SUSY model that shuts off all the questions. If you ask more questions, I'll show you this one. Anyways, the requirement, no, just kidding. Okay, so it is pretty natural to have this flat potential. And the requirement of a sustained thermal inflation implies a large gravitational. And get to the story. So the story is that the second stage of inflation is sustained by some thermal correction. And the thermal correction goes like some coupling this word times now when this term wins, you are trapped at the origin. When this term wins. Okay, and so the inflation starts when the inflation will start when this vacuum energy is bigger than temperature. Okay, so it starts at the temperature of square root of m1 v1, and the inflation ends when this term stops to dominate. Okay, and when the second order phase transition happens. Okay, so that's when the inflation ends, and that's also when the second stage of phase transition happens. That's when the domain will expand.
And this temperature came from reheating of the first stage?
Yeah. This is after the end of, yeah, the first.
And I'm just curious, what are the scales here?
Yeah, this is a free parameter at the moment. All I requires is that this is m1 square v square. The v1 is much less than v2. Okay, and the reheating temperature is presumably large enough so that this term can be. Okay.
But then all the density fluctuations that we have in the CMB are all coming from the second period, right?
No, this is very small scales. This is very late. This is small scales.
So this period of inflation is very short?
Let's say 10 equal.
Okay.
So, in fact, yeah. So this is the estimate of the. So this is what I just said on the previous stage. That there is a beginning time and there's end time, and there's a number of people, which is this, which depends on the parameter. That's the number equal that you have for the thermal inflation. And for sustained thermal inflation, you need this to be bigger than that. Okay, not too much bigger. Just need several equal the 10. Okay. And but this does mean that and this is much less than this, and if you put it back, but from the formula that we estimated earlier, but this does imply also larger gravitational wave. Okay, so this is just to show you, it goes into some detail that this scenario is reasonable.
But does it solve any problem though, this thermal inflation?
That's well.
Produce the gravitational wave? Except, I mean,
I think
besides producing a signal.
Yeah, I think in SUSY, it was in the early history was invented to solve moduli problem.
Exactly, because
Yeah.
I thought this was invented
Yeah.
to dilute if you have a big entropy.
Yeah.
dump,
Yeah. So
and this will dilute it again, right? So that's kind
Yeah.
of what you're thinking.
Yeah, but I'm not considering the moduli problem.
Yeah.
Yeah. Okay, so this is again what's going to happen in this scenario. So again, this is my diagram with many Hubble patches, and during inflation, I'm going to make strings, and the inflation is going to stretch the space time so that to make the string far away from each other. Okay, that's what the inflation does, and then the second phase transition happens. I'm starting to make walls. I use shaded region here, but after inflation, right? After inflation, the Hubble starts to grow. Okay, it starts to catch up with my. I have this much bigger. I start out with some structure that's much bigger than the Hubble volume, but the Hubble will start to catch up. Okay, so let's say I'm just. Let's say I have this kind of picture, and And now you can imagine this will, once it enters the Hubble, the causal physics start to work on this string wall network. It will start to reconnect, rearrange themselves into a more reasonable scenario, reasonable structure. And for example, these can become a disk, the disk that I showed you earlier. Okay, something like this. And this will become a little strip. And some of the strip can align together, making a longer strip. Okay. So this became qualitatively like a string, but with some width. Okay. With determined by the planned by the wall. And these kind of again behave like a string, so like they enter into this typical scaling scenario, scaling regime, and then it can cut itself, start to make rings, just like the string. And yeah, so there are these objects. I have these disks, I have rings and strips and so on. Okay, should I finish soon? Okay, so I don't have time to go through there. It's also quite easy to estimate just based on the simple analysis I showed you, to try to derive the spectrum of the radiation of this. So the upshot is that it's different from the strings because it has a width, and that the wall modes start to dissipate first, and then it will dissipate like a string. And the disk will also have a characteristic spectrum because it radiates. So let me know that, yeah, again, this is the picture is that for disk is oscillated and then collapse. And just based on a simple picture, you can try to estimate what the spectrum look like. And during the oscillation period, it will go like a K cube, and later because the disk starts to shrink, will go like I'm sorry, I don't have time to go through all of this. Yeah, so this is a typical spectrum of this. You can have multiple components. So this is coming from the disk, and this is coming from these lines are coming from the rings. So the real spectrum is you superimpose all of them on top of each other. They have all these contributions. And yeah, so if you're curious, these are some of the sample parameters. The string and the first for this picture, the first phase position happens at the 10 to the 13 DeV. The scale is 10 to the 13 DeV. String wall tension is 10 to the 6, and so on. And again, I don't have time to go into this. If so far, I'm assuming this picture is it's a global string. It's a gauged string, so it doesn't radiate anything else other than gravitation. No way. But if it also radiates the glowstone, it has a different structure. It depends on the size of this object. Sometimes gravitational wave radiation dominates, sometimes glowstone dominates. Because glowstone radiation power is proportional to the wave. If this is the shape of the global. If you're interested, I can talk to you more later. Yeah, so these are just some benchmarks. So this is now I do have one that if you wanted to even account for the nanograph. Yeah, so this is and these are the three different scenarios. If you choose different parameters, and this is what the global string looks like. And I think I also have one that at the higher frequencies. So I just went through these two stories. There are many other possibilities. I don't have time to go through. You can think about the first order phase transition during inflation, and the second order phase transition during inflation. That the wall produced the domain wall, and they can just fluctuate and radiate during the inflation. And the axial rotation getting to kination by Pauly is a big expert on that, and also this can come from also the features on inflation. Although I think that some of these features doesn't think about how to really compute some of these. And there's another reference of this is that in the snow mass, like paper that I think the book is all about, and then we have a quick summary of what has been known, what kind of signals that's possible. Okay, so this is my conclusion. I think that the only I want to leave you the impression that it is possible that we are actually on the verge of the beginning of a new era. I'm actually quite convinced that's the case, and in which we have a new tool to see much deeper and much earlier into the early universe, and we were expecting more so observation of stochastic gravitational wave in the coming decades. And of course, it's harder and it depends on future instruments, and you know, it's a longer term prospect, but I think we may just be at the beginning of a very exciting time. So again, I give you two examples that reveal some of the interesting dynamics of your early universe. And yeah, looking forward to the future. Sorry for Thank you.
So we had already a bunch of questions. So additional questions? Does anyone have additional questions? I would ask you this. Many of the predictions that you have, they all have like a triangular form with peaking at a certain frequency. Suppose Wook and friends, the community work very hard, build the experiment, measure somehow stochastic or gravitational wave, and then they discover some characteristic bump at a certain frequency. Is there any way you can back engineer what it was? Like, because it could be, you know, early phase transition.
Yeah.
It could be second stage of inflation with all these little things, right? So that it just judging by your talk, the number of possibilities is huge, and maybe it's just like that. It's very hard to back engineer what it was, right?
So I think I don't have it on my slide. I'm sorry. Yeah. So the in my paper, in our paper. So the first answer is the detailed spectrum can be different. The power, the dependence. So although they all look like this, which is not surprising. Usually the gravitational wave signal is dominated by, you know, there's a characteristic time or scale its generation, right? So then there's some power law. But if you look into details, these powers are different. Okay. So I don't have a so you do have to. It's very longer term, so you do have to. But that's the kind of the handle that I think you have. Other than the fact that you have some, then that becomes a model dependent question. I'm making very minimal assumption. It has nothing to do with us. Right? So basically, but if these things really have some coupling to us, we have some additional. So this is a I wouldn't say, you know, this is certainly quite a futuristic, but I think I wouldn't say there's no hope, right? Because I mean, again, just like a CMD, at the beginning we have no information whatsoever. It's like
That's not exactly right. I mean, the CMB, when it was discovered, it was immediately known that the Big Bang theory was the right theory as opposed to steady state.
Yeah,
so
but
that was an immediate impact.
But you don't have that much detailed information to say anything about yeah.
Right, you don't have the anisotropic spectrum, but it was a.
But we learn a lot from the anisotropic spectrum. I'm just saying, I'm referring to that. We don't have anything. So if you let's say if you discover something like this, right? Imagine this doesn't map to a scale, roughly speaking, right? You immediately conclude there's something dynamics wise is happening in our universe that is not a standard model. You're very likely to guess a scale. Okay, of course, it's still some model dependent, but you can try to guess a scale out of it. Now, exactly what happens? Well, this is you know, there's always the question I need to measure better to understand. We cannot really go back in time, right? So.
Well, on that note, I mean, I saw the sort of sectors you were talking about were like DeSigo and BPO, which are decades out if they're built. I mean, nothing. As you said, I think the frequency, the PTAs are not. There's
but this is just you know I don't want to stress that the lines that I draw on this picture is the largest signal that I can imagine. Okay, I didn't try to optimize to get to the largest possible signal. Okay, so I just more like I wanted to show you what the shape looks like. Okay, so the lines, where it is depends a lot on the parameters I choose.
Are any of these models maybe have some polarization in the background that we could go after?
The polarization of the gravitational wave.
Yeah.
Not this kind of model. The model that I know that does that is you either have some helical couplings in the magnetic field or the universe or something along those. Yeah. Or you have some AR wedge R coupling. So that coupling is very hard to actually generate the observable gravitational wave from that coupling. Anyways, it's a longer story, but there's some serious limitations of that theory.
Great. There are no more questions. Let's thank LianTao.
We are.